Welcome to Algebra 2. Today we've got 10.3, two-way tables and probability. Now we saw a little glimpse at a two-way table at the end of section 10.2 that we just completed. This will take us much more in depth and show us how these tables really do help us organize our information. And really, if we can read these well, they do an excellent job of making calculating somewhat complex probabilities very, very organized and an easy process. So a two-way table, to actually go through and explain what they are and their usefulness, it's designed to take events that may overlap and sort it into categories. So this does the work of a Venn diagram, but it organizes the information in that diagram into categories. So here you can see a sample that there's a survey of 80 students. Some of them play an instrument, some of them speak a foreign language, some do both of those or have both of those abilities, and others have none of those abilities. So to organize this into a two-way diagram, we're going to use rows and columns to kind of put those numbers into place. So I'd like you to take a second and pause the video and try to fill in this table using the rows and columns with the information from the Venn diagram, and I'll check back in a couple seconds to show you where those numbers go. All right, so hopefully we've got our table all filled in, and let's take a look at the survey of 80 students and see if we can't fill this in with the correct numbers. So first thing I want to do is the 25 students that play an instrument, I'm just going to add up these numbers, the 9 that do neither of those activities, the 16 that overlap, and the 30. If I add all of those up, those equal the total number of students, the 80 that were surveyed. So I know that this 30 over here does not include the 16. Those are separate. So those labels really do just represent their areas on the Venn diagram. So now if we look in our table, how many students speak a foreign language and play an instrument? Well, there are 16 students that fit that category. They do both. How many speak a foreign language but do not play an instrument? Well, that's 30, part of that blue circle that doesn't overlap. And that leaves us with a total number of students of 46 that fulfill the requirement of that first row, that speak a foreign language. Now, do not speak a foreign language. Okay, well, if 46 of them speak a foreign language and there are only 80 total, I'm expecting 34 students total that do not speak a foreign language. So let's see, they don't speak a foreign language, but they do play an instrument. Well, that's where our 25 comes from. They do not speak a foreign language and do not play an instrument. That is the 9 that is outside of our Venn diagram. And sure enough, 25 plus 9 does equal 34. So the total number of students that do play an instrument, that gives us 41, just adding up that first column. And play an instrument, sure enough, we got the 25 in the that are just in the red circle, plus the 16 that are a part of both circles. That makes 41. How many do not play an instrument? Well, we've got 30 from the blue circle, the part that didn't overlap, and the 9 that are just outside. That gives us a total of 39 students that do not play an instrument. So now, if we've done our work correctly in this table of values, as we go across the bottom row, 41 plus 39, that equals 80. And going down this final column, 46 plus 34, that also equals 80, representing our 80 students total. So now you can see this two-way table is really nice because for a probability, I know that my sample space is 80 students total. So if I randomly choose a student, what's the probability that they do not play an instrument, but they do speak a foreign language? Okay, well, let's see. They don't play an instrument. So I'm looking in this second column here. But they do speak a foreign language. That's the first row. I know that that's 30 out of 80. So 30 over 80 would be that probability. So again, by doing a lot of the calculations early, setting up this table, the probabilities become much easier to interpret and calculate. But we must be careful with the language. And speaking of language, we do have some new vocabulary that goes along with two-way tables. And the tables are identifying frequency. How often do we get a person that says yes or says no or will attend or will not attend? So we're looking for how frequently these outcomes arise. And so our basic two-way table, like the one we just did in our startup at the beginning of the lesson, those are telling us joint frequencies. So those are the totals in each box. So each of these 4 white boxes, those represent joint frequencies. It's just like tallying up how many fit in each category. Okay, then the marginal frequency, that's what we get when we total up a row or a column. Okay, so that's kind of setting up a sample space, so to speak. Now we can also allow our table to tell us even more. We had talked about in our introduction with the Venn diagram, we talked about how that puts the sample space right there in the diagram for us. We can actually do that with each individual box. Since we have the sample space, and here's an example of adjusting this attending or not attending for juniors and seniors. By having a joint relative frequency, all we're doing is we're taking each individual box that we had before and putting that over the sample space to get a number between 0 and 1, a relative frequency for those occurrences in each box. Okay? And then this also translates into marginal relative frequencies when we total up those rows and those columns. And you can see with the little call-out boxes that they have there, this shows us not only can we figure out really quickly what the probability of each individual box occurring is, but also by the rows and columns, the probability of a person in each type of category. And we also have a really nice check here as well in this bottom corner, because we know that a probability must go from 0 to 1. If we're accounting for all possibilities, that should be a 1 every single time. So by finding the total possible outcomes all summed up, we should get a 1 in that right-hand corner when we're looking at relative frequencies. Keyword there, though, is relative. And the last thing is conditional relative frequency. So here, it depends on the data whether we're using the sum of a row or a column, but we're taking the joint relative frequencies from before, and then we're putting them over a marginal relative frequency, in this case using the total for each row. So if we go back to that last slide really quickly, you can see our first row had a total of 0.482 over here on the right. When we do our conditional, that becomes our bottom in this quotient that we're doing here. So now looking at each row, what this is telling us, and you can see they've pointed this out in the bottom right entry. So given that a student is a senior, that was the total that's making our denominator, conditional relative frequency that they're not attending is found by taking that quotient. So now we can break things up into givens as well. So those dependent probabilities, things like that, all coming together here in these two-way diagrams. It does show us quite a bit. Our first task, complete the two-way table. So being able to navigate the totals and fill in a table, even if we're not given expressly or explicitly every single entry. So for the first one, you can see that we've got students and teachers that were surveyed. Some responded yes, some responded no. Okay, so we need to fill in the rest of this table. All right, well, this first entry, I know that there were 49 total no's. 7 of those no's came from teachers. That means 42 of the no's must have come from students. Well, then going across the top, I know that students, if 56 said yes and 42 said no, that means 98 total students were surveyed. Okay, going across the next row, teachers, some said yes, 7 said no. There were a total of 10 teachers that were surveyed. That means 3 of them had to say yes. And then going down our columns, 52 students said yes, 3 teachers said yes. That means 59 total yeses were totaled up. And then we should have the same sum going across this bottom row and down this column. 98 plus 10 is 108, and 59 plus 49 is also 108. So we know we've done that correctly. So again, even if our word problem or whatever prompt we were given, even if it didn't give us the full story, by setting up the table, we can use clues from the surrounding numbers to help fill in the remainder. Very efficient way of communicating information. Next one. Here we have no table given at the start, but they're giving us information. A survey asks 60 teachers and 48 parents whether school uniforms reduce distractions in school. Of those, 49 teachers and 18 parents say uniforms reduce distractions in school, so they answered yes. Organize these results in a two-way table, then find and interpret the marginal frequencies. All right. Well, let's get this thing set up. I know that, let's see, the response was a yes, they reduce distractions, or no, they do not reduce distractions. So those were the two possible responses to this survey. I know that people that were involved, we had teachers, and we had parents. And then we're going to be able to total up teachers, parents, total numbers of yes votes, total numbers of no votes, and then total number of votes, period. So let's see what we can fill in based on the clue we're given. Okay, 60 teachers and 48 parents. Okay, so that's total number of teachers is 60, 48 parents total. That's 108 total responses to this survey. So we can fill that in. 49 teachers say that uniforms do reduce distractions. So that would be a 49 for teachers voting yes, 18 for parents voting yes. That means that there are, what is that going to be? 67 total yes votes. Well, if 49 teachers voted yes, and there were 60 total that voted, that means 11 of them had to say no. And with parents, 48 of them voted, 18 said yes, that means 30 had to say no. And if we total up that row, 11 and 30 is 41 total no votes. Okay, just a quick check, adding down this final column, 67 and 41 does equal 108, just like 60 plus 48 did across that bottom row. So we know we've accounted for all of the data in the table. Now we need to find and interpret the marginal frequencies. It does not say relative, so I don't need to do any division here, but my marginal frequencies are these totals. All right, so this marginal frequency says that of the 108 people surveyed, oops, forgot the V there. $67 said yes. And then for the 41 of the 108 surveyed, 41 said no. Uniforms do not reduce distractions. Okay, and then across the bottom of the 108 surveyed, 60 were teachers, and of the 108 surveyed, 48 were parents. I really like these exercises, even though they're not that mathematically difficult, really forcing you to look at what the table is meaning. And if we have a firm grasp on that, it really makes the math part of this very easy. So realizing what those totals are representing definitely is going to pay off for us in the long run. Okay, for the next one, looks like I'm going to have to get my recording window out of the way. So here we are given a two-way table, and we're going to adjust that to show the joint and marginal relative frequencies. So now we're going to incorporate the sample space in here, and notice that everything is out of 410 total surveys taken, I guess you could say. So all we're going to do is we're going to take each of our joint frequencies in the white boxes up here, and we're going to put each of them over 410 to find those relative frequencies. And that will give us all of the joint relative frequencies. Then for the marginal ones, we are going to do the exact same work, but just with our totals. And if we do this work correctly, we should end up with a 1 down in the bottom right-hand corner of our relative frequency two-way table. So let's see what we get. So for number 8, here when I do that math, 62 divided by 410, I get 0.151. And for female, 6 divided by 410, I get 0.015. And 3 decimal places are a pretty good rounding point to use for these frequency tables. All right, for the next one, average males, 275 divided by 410, I get 0.67. And 0.059. Next row, 0.098. And James Bond, 0.007. So those are all of our joint relative frequencies. And now if we sum up those columns, we should get the same thing as doing the work shown up here. Taking 377 divided by 410, I should get the same thing as if I had just added up that column to begin with. So that's another nice check to see if maybe you misplaced a decimal point or some of your calculations were off. So here's what I got as a result of my calculations. I got 0.919, 0.081 across that bottom row. And down the last column, I get 0.166, 0.729, and 0.105. And again, we can do a quick check adding down this column and adding across this row, making sure that I arrive at a 1. Obviously, there may be a little bit of rounding there, but making sure that I arrive at a 1 for that, that total in the bottom right. Okay, so there we have arranged it, and now just realize that now I know that the probability of a average female is 0.059, you know, if I'm just randomly choosing somebody along the way. And who knows what this table is actually representing, but very easy to grab those probabilities because all of the data is arranged for us. Very cool. All right, our next example. In a survey, 49 people received a flu vaccine before the flu season. 63 people did not receive the vaccine. Of those who did receive the vaccine, 16 people still got the flu. Of those who did not, 17 got the flu. Make a two-way table that shows the joint and marginal relative frequencies. Okay. So let's set up our table. We've got people that got the flu and those who did not get the flu. This would be like responding yes or no. All right. Then we got people that did receive the vaccine and people that did not receive the vaccine. Okay, so here is our two-way table. We'll fill that in and then we'll calculate some totals. There we go. And you could tell they're not giving us enough numbers in their prompt to fill in this table completely, but hopefully it's enough that we can use the clues around the table to kind of fill that in. All right, so in a survey, 49 people received a flu vaccine. Okay, so that's going to be a marginal frequency of people that got a vaccine, and 63 people did not. That means that we had 112 people total that participated in this survey. Of those who received the flu vaccine, 16 people got the flu. So got the vaccine and got the flu, the unfortunate 16. Put that in the correct row and column in our table. Of those who did not receive the vaccine, 17 got the flu. So no vaccine, they rolled the dice, they still got the flu. That's 17 for that particular row and column. Okay, so for that marginal frequency, people that got the flu, that's 33 people. All right, let's see if we can't fill in the remainder of our table, because we've already entered in all the numbers that we were given. All right, 49 people got the flu vaccine. We know 16 of them, unfortunately, got the flu. That means that 33 of them were vaccinated, and it worked. They did not get the flu. Now let's look at the next column. 63 people did not get the vaccine, 17 of which did get the flu. That means there were 46 that didn't get vaccinated but happened not to get the flu anyway. Okay, and then for our final marginal frequency going across that no flu row, 33 that got the vaccine didn't get the flu. 46 that didn't get the vaccine happened to not get the flu as well. That's 79 total people that are fluless. All right, so there's our two-way table filled in with just the joint and marginal frequencies, but we want joint and marginal relative frequencies. So we had to calculate this number right here, 112, to find out the total number of people that were involved in this survey. And now it's just a matter of going through and dividing all of our other entries, both joint and marginal, by that 112 to find their relative frequencies. Okay, so 16 divided by 112, I get 0.143. 33 divided by 112, I get 0.295. And then 49 divided by 112, I get 0.438. Okay, and just a quick check, if I add up 0.143 and 0.295, does that agree with the total at the bottom of that column? Yes, it does. Next column for the no vaccine, we have 0.152, 17 divided by 112, then 0.411, and then 0.562 to round off that column. And if I do a quick addition, yeah, they don't necessarily add up, but that's more than likely just a rounding issue on my part. Okay, and then lastly, our final column, 33 divided by 112, that's 0.295. 79 divided by 112, that's 0.705. And if we just do our quick check, adding across the bottom column or across the bottom row and down the right-hand column, I do reach a total of 1. So I can have some confidence in these marginal and joint relative frequencies to know that I could quickly find the probability of somebody that got the flu and was vaccinated. Or, you know, and this, you can see how this would be really useful. Flu vaccine is a really good choice for an example, because this is something that you probably want to know in your area, right? You know, how effective is the flu vaccine at, you know, keeping people from getting the flu? Very nice way of organizing the results of the survey. And finally, I have to move this over here. Oh, look at that, just fits. A researcher surveys random sample of high school students in 7 states. The survey asks whether students plan to stay in their home state after graduating high school, or they want to leave. The results given as joint relative frequencies are shown in the two-way table. All right, so now realize they've already done the work that we just did in our flu vaccine example for us. So we're working with all of these little probabilities to answer parts A, B, and C down below. Letter A. This one says, what's the probability that a randomly selected student who lives in Nebraska plans to stay in his or her home state? So let's put that into our probability terminology here. That's the probability of staying given that they live in Nebraska. Okay, so the probability that they want to stay given that they live in Nebraska. Well, what that's going to equal is the probability of staying and being in Nebraska over the probability that they are just in Nebraska. All right, so from our two-way table, that's pretty easy to spot, right? So stay and live in Nebraska, that's 0.044, over just the probability that they are in Nebraska, that's the sum of those two. Everybody surveyed in Nebraska, that's 0.044 plus 0.4. And when we crunch those numbers, what we get is 0.099. Okay, and you can see that the math was very easy, and the table really helped us locate what we needed to fit into that probability we were trying to answer. Let's look at letter B. What's the probability that a randomly selected student who does not plan to stay in his or her home state after graduation lives in North Carolina? So here, we want the probability of someone being in North Carolina given that they want to leave. All right, well, what that's going to equal is the probability of being in North Carolina and wanting to leave over the probability that they want to leave, regardless of state. Okay, so North Carolina and they want to leave. Okay, so that's this 0.193 over all of the people that wanted to leave. That's 0.4 plus 0.193 plus 0.256. That gives me a result of 0.2273, 0.227. And then lastly, part C. Determine whether planning to stay in their home state and living in Nebraska are independent events. So up until this point, we talked about dependent and independent events. We said that we were mainly dealing with coin flips and dice rolls and drawing marbles out of a bag, things that were pretty easy to tell if they were changing our sample space. It's not so easy to tell. Well, if we think about the probabilities, this should make sense. There's a quick check. Is the probability of staying, just in general, is that the same as the probability of staying given that you're in Nebraska? In other words, is it the same thing regardless of whether or not we live in Nebraska? Okay, so we'll calculate these. Probability of just staying in general is going to equal the sum of all the people that answered yes so that's 0.044 plus 0.051 plus 0.056. That gives me, what's that going to be? 1.07, 0.151. And then the other part, probability of staying given that you're in Nebraska, well, that's the probability of staying and being in Nebraska over the probability of just being in Nebraska. Okay, stay and be in Nebraska, that's 0.044. Over probability of being in Nebraska, that's 0.444. which we found in part A is 0.099. So since those two probabilities are different, in other words, just staying as a result of the survey is not the same as staying given that you're in Nebraska. We know that they are not independent events. So a little bit more work, and this test for independent, the first line in green there, it really does make sense, and then it allows us to mathematically use the table to our advantage and make some quick calculations to answer that question. But understanding that first line, is the probability of just staying the same as the probability of staying given that you're in a certain state, in this case Nebraska? That would indicate that they are independent of one another. In this case, they definitely are not. Here's a look at your assignment for this section, and that does it for 10.3.